Hello everyone, how are you doing? This is the second video that we're going to talk about vector field. Vector field is, the notation is mostly bold-faced letter F, and it is uppercase, and you can have a vector field in a plane or you can have a vector field in a space. 2 component, 3 component. Vector field can come in different variety. It could become many vectors emanating from a point, therefore they are going away. This is maybe called divergence. This one, maybe all the vectors coming toward a point, therefore this is called a central force, like everybody attract to a center of the earth. Sometimes a vector field could come toward some of them come toward the point, some of them go out. It could come in a slant position, going up or going down. We're not going to discuss many different types, but we're going to discuss a couple of them. One of them, maybe I write a vector field such as x comma y. Therefore somebody said, well, this looks like a gradient. Can I call a vector field a gradient? I said no. Maybe a gradient can call a vector field, but vector field is a vector field. But if that vector field become exactly similar to gradient of some function, that vector field called a conservative force. Somebody said, is this conservative? Well, that's the partial with respect to x. Therefore, I'm going to undo it. That's the partial derivative with respect to y. I'm going to undo it. Therefore, I bet you there was a function which it was 1/2 x squared plus 1/2 y squared, that if I find its gradient, it will become x and a y. Oh, that vector field is just like this gradient. Therefore, you can call this gradient a vector field. And what kind of a vector field it is a conservative. But if I write f of x, y here as a vector field, and I call this one a negative y comma x, but if you take, this is a partial, this is pretty much, this is an R2, therefore vector, this is the x component and that's the y component. And if you want to call it a gradient, that should become partial derivative of x, if you want to call it a gradient. And if you want to call this one a gradient, that should become partial derivative with respect to y. Therefore, if I undo respect to x is this. If I undo respect to y is this. Therefore, if I call that function xy, you have to combine these two because they are different. And when you combine them, you get 0. And the partial derivative of 0 respect to x is not a negative y, and respect to y is not x. Therefore, this does not represent gradient of any function. That's called non-conservative force. Okay, we talk about conservative, non-conservative, but let's go back talk about the vector field. Let's say my vector field is a series of vectors which you assign the order pair on the plane to these vectors, and at that point you're going to have a vector like 0, 0. 1 and a 0, you have 1. 2 and a 0, you have vector with magnitude of 2. 3 and a 0, you have a vector with a magnitude of 3. But somebody said, do they overlap? No. Vector field means you have to draw the field first. Maybe your field is look like this. Maybe your field is look like this. Maybe your field is like this. First, you have to find out how is your field look like. And how do you find your field? You find the magnitude of your vector field, the magnitude, and that magnitude always is going to become magnitude, should be a number, is a scalar number. I'll call it C. Then, using these C equal to square root of x squared plus y squared, you can create level curve on x and a y. Therefore, if C is 0, when you square both sides, you get a 0. C can be 0.1, 0.2, 0.3, 0.4, 0.5, 0.001, 2.1. But I'm going to find some easy numbers and I'm going to get it over. If C is 1, I'm going to square both sides. I get a unit circle. Therefore, when it's 1, 1, 1, 1, I get a unit circle. If C become 2, and when I square this one, that's become a 4. Therefore, that become a unit circle with a radius of 2. And that's enough. Say, okay, I got my field. And tell me, what was your vector? My vector is x comma y. Therefore, your vector field is x comma y. For 0, 0, you get that one. Let's go here. This is 1 and 0. 1 and 0, you get 1 and 0. You have a vector with the magnitude of 1. What is this one right here? That's radical 2 over 2, radical 2 over 2. That become that one. Here become 0, the order pair is 0 and 1. The vector field, the vector is 0 and 1. That's the vector with a magnitude of 1. That's the point on the unit circle, and I'm going to call it negative radical 2 over 2 and radical 2 over 2. Then when I put it inside my vector, you get negative radical 2 over 2, become 0.74, and plus radical 2 over 2, that become exactly a vector with a magnitude of 1. In here is negative 1 and 0, you get a vector with a magnitude of 1. Here is 0, negative 1, this. Therefore, you better see that every one of these vectors are normal to the level curve. And somebody said, why? Because this is a conservative. And the conservative has a potential function. And the potential function is gradient is similar to this vector field. Therefore, that gradient is a vector field, and we know the gradient is always normal to the level curve. Then if you have a conservative force, means you have a vector field and you can create a potential function which is gradient is exactly look like a vector field, their vector is going to be normal to the level curve. This one become magnitude of 2. That's become magnitude of 2. That's become magnitude of 2. That's become magnitude of 2. That become magnitude of 2. That's a magnitude of 2. Then every one of them all normal to the level curve, and as you get away from a center, the magnitude gets bigger and bigger and bigger. And it getting away means these are called radial. Radial means it has some kind of a speed. And look at the speed right here. The speed gets larger and larger and larger. Oh, let me not go to the next example and come back to this. If I have a level curve right here, but my vectors are like this, just tangent to my level curve, not normal. This is called circulation. You are rotating. This one called divergence. Means in here there is no circulation. Means your circulation is zero. You're not rotating. This one is a circulation, but I don't know if I'm circulating at the same time if I'm getting away from my center point. If I'm inside a jacuzzi and jacuzzi has a wall and the water is only rotating, therefore I have only, what do I have only? I have rotation. But if there is a pump in here and it circulates the water, but there is not a wall, you are middle of an ocean, oh, you can have a boat in here, but it rotates you, rotates you, rotates you, and you gradually getting away from the center. Therefore, this has a circulation, and at the same time, it has a divergence. Then most of the vector field are either circulations, divergence called a radian, this is called circulation, or the combination of these two. Somebody said, okay, tell me what is the circulation look like. If I write, and please remember, maybe tomorrow you go to a certain textbook and certain textbook called the circulation rotation. Don't criticize me. There are many, every instructors, they use different name for the textbook, looks different. I'm going to have a negative y and I'm going to have an x. That is my vector field. Somebody said, is that a conservative? I said, I don't know. If it's conservative, it should have a potential function. Potential function is going to have a gradient. Then if I consider this one the gradient of that function, that should become partial with respect to x, partial with respect to y. Undo this respect to x is negative yx. Undo this one respect to y, xy. These are different. They are not the same that you write it once. Then potential function is xy minus xy. No. The partial derivative of 0 respect to x is not this. The partial derivative of y of the 0 is not x. Therefore, this is a vector field. There is no gradient that it become look like this. Therefore, this is non-conservative. And let's think about it. What is the magnitude of that vector field? The magnitude of that vector field is the square root of y squared plus x squared. I'm going to make my magnitude a constant, and I'm going to plus 0 in here. Then I get a point. Okay, I got a point. If I put 1, I get a unit circle. Is the same as the previous one. Unit circle, circle with a radius of 2, and circle with a radius of 3. Not always level curve is a circle, but we're doing some easier stuff right now. Somebody said, what is this? This is 1, 0, 2, 0, 3, 0. Okay. Y is 0, x is 1. Therefore, you're going to have 0, 1. 0, 1 is this. In here is 0, 1. X is 0, x is 0, y is negative 1. Therefore, you have a negative 1 and 0. That's a negative 1. If I put radical 2 over 2 over radical 2 over 2, that become x become negative radical 2 over 2. That become a radical 2 over 2. That become my vector. I bet you this one is going to be this. This one is going to be this. This one is going to be this. This one is going to be look like this. Every one of these vectors are tangent to my level curve. And all my unit tangent have the same direction as my path. But in this one, which we had in previous one, circulation was 0. And all the vectors were normal. Therefore, from today, you have to know 2 words. One called divergence. What is the divergence of that vector field? I bet you that vector field gonna have a different speed at the different order pair. And in here I'm gonna say, what is my circulation? Maybe in here I said circulation is just like a piece of wire. And maybe that circulation gonna have some curl into it. Then sometime they said how much curl that vector field it has at a certain point. What does it mean, a curve? Means how fast this curve is turning. You got to tell me how fast this curve is turning. There are many, many points in this curve, and you have to tell me how fast they are turning. Therefore, today I'm going to talk about 2 things. Number 1, the divergence of a vector field. And number 2, the curl of a vector field. But please pay attention. When I talk about divergence, divergence is sound like a speed. And a speed is just a number, is on a scalar. Therefore, I got to do something with a vector, which is my vector field, do something with it, that I get a scalar quantity. What is that something? I got to do dot product. Dot product give you a scalar. But I don't know what I'm going to dot product with. But curl is a rotation. At any given point, you have different direction. Therefore, curl is not a scalar because direction is continuously changing. Then what should I do with my vector field that it give me a vector? You got to do cross product. Okay, I'm 100% with you. Let's go back and look at this one. That was my vector field. And that vector field, you know the curl is 0, but it does have a divergence. And I'm going to ask you, what is the divergence? If you have a vector field of x and a y, you got to dot it with another vector. And another vector, please pay attention to what I'm saying right here. When I write d over dx, and I ask a student what this represent, they said this one is a surgeon. It does surgery. And I'm going to say, how about this one? This is also a surgeon too. But you could have a surgeon to operate on the heart. Some surgeon do on the brain. This surgeon, whatever function you give to, it's gonna take its derivative. And this surgeon, whatever function you give to, it's gonna find its antiderivative. Therefore, these two surgeons, the only thing they do operation. Therefore, d over dx called an operator. The integral of a dx with a blank integrand called an operator. In here, I'm going to have an operator. And my operator is going to be the partial derivative respect to x, partial derivative respect to y. I said these are operators. You don't put no function, just an operator. Therefore, you only operated with, dotted with the operator. And what is the partial derivative of x respect to x? 1. What is the partial derivative of y respect to y? Is 1. Therefore, this is telling you, at any given point, the speed is a fixed speed, and that speed is 2. Somebody said, are you kidding me? I said, okay, right here, x, y, z. I'm going to write x squared, y squared, plus xz plus z cubed. And I did it 100% wrong. I'm supposed to have a vector field. That's the vector field. And they're going to say, what is the divergence of that vector field at any given point? X squared, y squared, xz, z cubed y. You dotted with the operator. But in here, because it's in R3, you need 3 operators. What is the partial derivative with respect to x? 2xy squared. What is the partial derivative with respect to y? 0. What is the partial derivative with respect to z? 3z squared y. That is the divergence of the vector field at any given point. Right now, somebody say, what happens if the point is 1, 1, and a 1? At that specific point, the speed is 2 plus 3 is 5. Remember divergence, feet cube volume per second. Somebody said, how about at the point of 2, negative 1, and 3? 2 times 2 is 4. Negative 1 squared is 1. You have a 4. 3 times 9, 27. 27 times negative 1, negative 27. Therefore, your speed is reduces by 23 feet cubed per second. Therefore, your divergence could be positive and it could be negative. Is it possible to become the divergence is 0? Well, you did have a circulation here. And the circulation was negative y, x. You dotted with 2 operators. And you say partial derivative with respect to x is 0, partial derivative with respect to y is 0. Yes, the divergence is 0. Means in here you have only circulation. But you asked, how do you find the amount, the rotation or the curl? I said, okay. When you talk about curl has a x, y, and a z. Curl is always going to happen in 3 dimensions. But somebody said, what happens if it's in R2? Then you have to make your z component 0. Therefore, a curl of a vector field is, okay, do you want to do the rotation one, which is right here? Negative y comma x, negative y, x, and I make my 0 is 0. Why? Because I have to do cross product. Cross product of a negative y, x, and a 0, it has to be in R3. I need a partial derivative respect to x, partial derivative respect to y, partial derivative respect to z. And how do you find the curl of the vector f, x, y, z? Really, my z is 0 right here. You write your I component, you write your j component, you write your k component. In here, I write negative y, I write x, and I write 0. Let me do something else. Let me put that negative y, x, and 0 here, and put my operator here. Is a lot easier. Right now, what is your I component? Eliminate, eliminate. 0, 0. Minus a j. 0, 0. Plus a k. Partial with respect to x is 1. Partial with respect to y is negative 1. But remember, I have two negative because I'm going backward. Minus a negative 1. And what is your curl? Your curl is 2k. What did that mean? Mean at any given point, that's your z-axis. That's your z-axis. It is rotating. It is rotating. And if you want to know what is that one right here, you have to go to z, and that's become right here and right here and right here. Therefore, it does have a circulation. The curl is always constant, always constant. That's your constant. And somebody said, what is the magnitude of the curl of the f? It's 2 feet cubed per second. That's how fast it's rotating. Somebody said, okay, let's have a problem. But I'm going to cheat on my problem. I'm going to start with a function, and I'm going to write x squared yz plus xy plus a z. This is a potential function. The gradient of this one could represent a vector field. Therefore, I write my vector field as the gradient of that function and as 2xyz plus a y, x squared z plus a x, x squared y plus a 1. But somebody said, I need the curl of the vector f. You need an I, you need a j, you need a k. But you do need an operator. And right now, I'm going to ask you a favor. What are these? These are partial derivative. Can I call this partial with respect to x, partial with respect to y, partial with respect to z? 100% you can call it because it is coming from a potential function. But if this one does not have a potential function, you cannot call this one f of partial derivative of x, partial derivative of y, partial derivative of z. Therefore, this is the partial with respect to x. But I want you to give me a hint, please. If I go find my I component, this is partial derivative of y, but this was also partial derivative of z. Pretty much you're doing f of zy, because this is partial with respect to z. That's what it is. But you're taking is partial with respect to y. And remember, in previous chapter we said order doesn't matter. F of zy and f of yz are the same. Okay, remember that. Therefore, the partial with respect to y is x squared. That's it. Minus this one is a partial derivative of the y. Oh, partial derivative of the y. But you're doing it with respect to a z. Oh, you already got zy. Therefore, that one also should become x squared. Let me, if I am right. That's x squared. And this is 0. Okay. Wait till the end. J. Remember, this is partial derivative with respect to z. This is partial derivative with respect to x. Pretty much you're doing f of zx. And I bet you that should become the same as f of xz. Let's see. This one respect to x is 2xy. But this one respect to z is 2xy. But I have to subtract. Plus k. Remember, this is my k, but this is partial derivative with respect to y. But right now I'm taking partial derivative with respect to x. That should be the same as partial derivative of x respect to y. Let me see. Respect to x is 2xz. But respect to y is 2xz. And what is the curl of the function? 0. And tell me why. Because if you do have a conservative force, those x component, y component, z component are already a partial derivative. Then you taking the derivative of the partial derivative of the partial derivative, but in a different what? Different order. If it's respect to x, you do respect to y. If it's y, you do respect to z. And because the order doesn't matter, you get to 0. Then this is telling you that in here, right here, I want you to watch. This one right here. I did found the curl. I'm going to find the curl of that vector, which is I, j, k, partial x, partial y, partial z, and this one is going to become x, y, z. The I component is 0. The j component is 0. The k component is 0. Oh, the curl of that one is f is 0. I say this is 100% divergence. Why? Because this was conservative. And conservative, the vector field, it is a gradient and is normal to the level curve. There is no rotation. Then from today you have to know that a conservative force, its curl is always going to become 0. If it's a conservative, the curl is 0. And you do have a divergence. Then somebody said, oh, do I have to find the curl of the vector field, and if it becomes 0, I call it conservative? I said, no. Just go to this vector field and see if this order works. If this is partial derivative with respect to x, do it with respect to y, and it's 0. If this is partial derivative with respect to y, do it with respect to x, and that's 0 because they are the same. In here, I want to know if this is conservative. If it's a conservative, that should be partial derivative with respect to x. And then if you do it with respect to a y, it's a -1. And if I take this one as a gradient, that's partial respect to y, right now respect to x is a 1. Is 1 and a negative 1 are the same? No, that's non-conservative. Therefore, from now on, if I give you a vector field, and I said, is this vector field conservative? You said, give me a second. If it's a conservative, this should be a gradient. Gradient means this is partial with respect to x. Let me do it with respect to y, is x squared. If this is a gradient, that should be partial with respect to y. Then let me do it with respect to x, is 3x squared y. I'm sorry, they are not the same. That's not a conservative force. Therefore, in this video, we talk about the radial, the circulation. We talk about the curl of a vector, which you have to cross it with an operator. And we talk about the divergence, which you have to dot it with an operator. See you in the next video.